So we're going to do some practice problems with the mirror and magnification equations in this video, but before I do that I want to talk a little bit about sign conventions. And we sort of ended our last video with this image, right? And we could, to check our work, we can always think about, okay, what does this mean and does that make sense with what I've learned about what sort of images concave mirrors forms? But we started talking about, like, what does a positive or negative height mean? And we said that a positive height means that it is above the principal axis, and a negative height means that it is inverted or below the principal axis. And we theoretically could have a positive or a negative distance, and as well as a positive and negative focal length. So I want to talk about what those are. And remember in physics that a positive or negative sign in front of a value tends to imply direction. And so what could these directions mean when it comes to distance? Okay. So, and we have distances of objects and images, but this applies to both. So if you have a positive distance, it is in front of the mirror. Whatever that side is in terms of front of the mirror, for a concave mirror, it's going to be on the same side as the focal length and center of curvature. On a convex mirror, it'll actually be on the opposite side of sort of outside of the sphere. But whatever in front of the mirror is, that is positive distance. Negative distance is behind the mirror. So any virtual image will have a negative distance, and any real image will have a positive distance. For height of the image, a positive height means that it is above the principal axis. And negative height means it is below, and usually this means upright. But it does, of course, depend on your object, too. Below. Principal axis. And last but not least, we could have a positive or negative focal length, and we're not going to get too into this, but I'll just mention it here for you to have in your notes. A positive focal length means that the focal length, it's like distance, right? Focal length and distance are both distance values along sort of that principal axis. So a positive focal length, in a similar way to a positive distance was in front of the mirror, we could say a positive focal length is where the focal length is also in front of the mirror. And this is frequently seen in concave mirror situations, right? Where your object is here and your focal length f is in front of the mirror. A negative focal length, however, is where the focal length is behind the mirror. And this exists in a convex mirror. We haven't really talked about convex mirrors yet, but we will. And so you can imagine that in a convex mirror, right? Here's the convex mirror. Yep. The focal point is here, but the objects are all over here, right? And so the focal length is on the area behind the mirror, and so that creates a negative focal length. So how do we use these? Let's do another practice problem for concave mirror. A 4 centimeter tall light bulb is placed a distance of 8.3 centimeters away from a concave mirror with a focal length of 15.2. So this is exactly the same as before in another video, but just where the object exists is different. Determine the image distance and image size. So again, let's identify what we have. We have our object height is 4 centimeters. It's a little too many bumps there. Centimeters. Our object distance is 8.3 centimeters. And our focal length is 15.2 centimeters. We don't know our image distance, and we don't know our image height. So, what do? Same process as last time. We'll use our mirror equation. Filling in what we know. Sorry. And if we solve that, we end up getting an image distance of negative 18.3 centimeters. What does this mean? This means a negative image distance means that the object is behind the mirror, and we'll talk about that in a bit. Okay? Using the magnification equation, we can fill that in with what we know. And if we were to solve that for our image height, we get that our image height is 8.82 centimeters. So we have our image height and our image distance. And so let's talk about this, right? Our image height has gone up. Our image distance is negative. And we know, let's think about this, right? We have our concave mirror and our focal length of 15.2, but our object is only a distance of 8.3 from the mirror. So that means our object is in front of the focal length, between the focal length and the mirror. Its height is a positive 4. And we got a negative value for image distance. That means that the image is behind the mirror, a value of 18.3 behind the mirror. And this makes sense because we know that images formed by an object that is in between the focal length and the mirror form virtual images behind the mirror. We also know that those images are upright, which makes sense because our image height was positive and it's enlarged, right? And all of these things make sense with what we got. So it's nice to be able to check our work. I'm not going to do this top one, but you could if you wanted to. I'm just going to focus on this bottom one because we're going to use this value for magnification. An inverted image is magnified by 2 when the object is placed 22 centimeters in front of a concave mirror. Determine image distance and focal length of that mirror. So we're doing a couple of different things here. So what does this magnified by 2 mean? That means that in the magnification equation you have that value m for the ratio. The magnification in this case is 2. Magnification is like 2 times. It doesn't really have a unit. Okay? It's a relationship. The object is placed 22 centimeters in front of the mirror. So our object distance is 22 centimeters. Determine image distance and focal length. Well, so let's look at our mirror equation. It is that our magnification equation. Our magnification equation states that the magnification is equal to the image height over the object height as well as the opposite of the image distance and the object distance. So I don't really need this internal section because I can just say, well, these two things are equal to each other, and that's all I really need to know because I want the image distance and the focal length. So my magnification is going to be equal to the opposite of my image distance over my object distance, and I can fill in that my magnification is 2. I do not know my image distance, but my object distance is 22 centimeters. And then this is easy enough to solve. My image distance is negative 44 centimeters. Okay, so what is the focal length of my mirror? Well, we can find the focal length of the mirror by doing our mirror equation. 1 over the focal length is equal to the 1 over the object distance over 1 over the image distance. But I'm solving here for focal length. So I can say 1 over the focal length is equal to (1 over 22 centimeters plus 1 over 44. Now, notice that this really should not be negative 44 centimeters. I know that we're producing an inverted image. An inverted means that my image is going to be upside down. If it is upside down, it is a real image, and that also means it's in front of the mirror. So why did I end up with a negative value for my distance? Well, that's because in this equation, usually an inverted image has a negative height, but therefore has a positive distance, or the other way around, a positive height means that it has a negative distance. But because we didn't do the relationship with height, I really should have gotten rid of this negative here. So this should really be positive 44 centimeters. So anyway, back to this equation. 1 over the focal length is equal to 0.068, and the focal length of this mirror ends up being 14.7 centimeters. And so there we found our image distance as well as our focal length. And you'll note that the focal length is enough such that the object ends up being placed between C and F, and we know that if an object is placed between C and F, it will be enlarged, it'll be real and inverted, and the image will be beyond C. And all of those things work out perfectly.